All right, good morning, everybody. So welcome to EE252 Electronic Design Devices and Circuits course. This is the first time we are meeting on this course. So I'll be uh, teaching you the bipolar junction transistors section. Professor Disala already covered the semiconductor physics and diodes, I believe. So I'm starting the BJT this section today. And after that, Dr. KRMN Ratnayaka will start his section on FETs as well as other sections. Okay, right. So, and so the way I plan to conduct the lectures, basically the first few lectures I plan to have live Zoom sessions, just like today, during our normal scheduled hours. But later on, I'm planning to upload my lectures beforehand. So I have some recorded lectures. They will be uploaded to the fields, and you are supposed to watch them either during the scheduled time or before that. Okay, and once a week or so we will have a discussion class so that we can go over the topics and clarify doubts, and maybe if necessary we can do a related question also, how to do a problem solving, how to solve a problem. Okay, so that way it will give us more time and flexibility to do a little bit more than what we have been doing if we had physical classes. Right, so you have the flexibility to watch the video whenever you have time, and that way I believe you will be and because we also get an opportunity to discuss these things, we can actually try additional problem solving also in the class during the discussion class. So make sure when you come to the discussion class, you go through the lecture and come up with questions so that we can discuss anything. Okay, so this is where I give you additional points, the bonus points. Okay, let's get started. Let me share my screen. Okay, now at any point, if you feel that my voice is not clear, please let me know it, okay? I can't see hands raised, but you can talk, but not among yourselves. You can just unmute your mic and say, we can't hear you, and I will try to address that, okay? All right, so we are going to talk about bipolar junction transistors, BJTs, as we know. Before we actually go into the actual BJTs, I want to review a little bit of semiconductor physics for diodes. I know which you have done in depth. Professor Visala might have done it a very good job at this, but I just want to make sure that I do not assume anything. So therefore, I'm going to cover a little bit of, not a lot, just what we need for the BJTs, okay? All right. So in order to understand the principle of operation of the BJT, before I talk about the BJT, let me first talk about the diode semiconductor physics. Okay, review of diode semiconductor physics. All right. So you know, a diode basically consists of two semiconductors. One is an N-type, the other is a P-type, right? You know, semiconductors are like silicon and germanium. The materials that are typically, these are not conductors, they are insulators. But by adding some dopant, in other words, an impurity which is from either the third or the fourth, third or the fifth uh, periodic table columns. So we add these. So what will happen is it will make either free, if you take a pure silicon, you have the same number of electrons as the protons, so there it's neutral, and none of the electrons are free to move around. They are covalently bonded to other atoms, so therefore it's an insulator. So is germanium. But when you add, let's say, a little bit of aluminum, right, which is basically in the third column, or something like phosphorus, which is in the fifth column, what it will do is there will be few atoms where you have one more electron. In the case of if you add a fifth column type like phosphorus, or you will have lack of electron to bind with the neighboring silicon, right? So therefore they will be called holes. So there will be, these will be doped. These are called doped semiconductors. They are conductive because of this unbonded electrons or holes. Actually, what supports the current conduction is electrons, but because there are holes, electrons can jump into these holes, and that also makes it conductive. Okay. So N-type and P-type semiconductors are conductors because of this availability of charge carriers. These charge carriers are either electrons in the case of N-type material and holes in the case of P-type material, right? But when you combine these material, we will see that combining doesn't mean that you make two different material semiconductors, one N-type and one P-type, then you bring these together. That is not how you create these junctions. But anyways, if you take these two types of material, we'll talk about how they are made in a minute, but maybe the next class. But when you bring these two together, the N-type will have some free electrons which are free to move about, and the P-type material will have some gaps or holes, so that electrons, there's lack of electrons, so they are called holes. So they are kind of like positively charged free charge carriers, right? Whereas electrons are negatively charged charge carriers. Now what will happen is, since electrons are free to move around and holes are there to fill, when you bring these two materials together, the free electrons will jump and fill the holes. So these additional electrons hanging around in the material will move to a neighboring positive neighboring space where you have one electron lacking, and they fill the space. So that what will happen is N-type material will become positively charged because you lose electrons, right? Because the electrons that were there were donated to the other side. So therefore the P-type will become negatively charged around the junction. Now more and more, as more and more electrons cross to the other side, there will it will develop what is called a charge bilayer, a positive charge on the N side and a negative charge on the P side, because you have more electrons in the P side now than the protons, and less number of electrons in the N side than the protons in the N-type material. So this will continue to happen until the electrons cannot overcome the repulsion due to this newly formed negative barrier, right? So because of that, there will become a dynamic equilibrium where some electrons jump to the other side, but they also reverse in the other direction because of this repulsion. Okay, so this layer, once these electrons move about, will have no charge carriers, because the charge carriers are the free electrons. Now they are on the other side, they jump to the other side and form this negative charge layer, and there are no free uh, electrons or holes in that small region, which we call the depletion layer. Depletion layer. Why do we call it depletion layer? It is depleted of charge carriers. Okay, it is depleted means you have removed. There is no charge carriers. So therefore, we call this depleted depletion layer. So this is the depletion layer. The depletion layer, because you don't have charge carriers, is highly non-conductive, because no charge carriers to support electric conduction. This is the depletion layer. Okay. So if you look at this kind of like, this is the diode. So the diode looks like this, right? You know, the symbol of the diode is like this. In the diode, if you have not connected it to anything, there is a depletion layer which prevents, because this depletion layer is highly non-conductive, though the rest of the substrate, the rest of the N and P material support conduction of electricity, because there is a insulated section, the depletion layer, it doesn't uh, provide support for uh, any electric conduction, right? So therefore, it is highly non-conductive. That is why the diode, as it is, doesn't conduct any electricity. Now, let me give some notes before I continue. So the same things that I mentioned, I will write down so that it serves as a note. N-type and P-type semiconductors are semiconductors are conductors due to the availability of charge carriers. They are basically electrons in N-type and holes in P-type. Okay, so they are conductors. But when a junction is formed, electrons in N-type fills some holes close to the junction in P-type. Because of this, a region where there are no charge carriers is created. Since this region is depleted of charge carriers, it is called the depletion region. There is no A here. Depletion region. Okay. Since there are no charge carriers, in the depletion region, it is highly non-conductive. The depletion region can be increased or decreased by applying an external electric field. Okay, so let's see how to do that. Now, depletion region, remember, it's this region where you have no charge carriers because electrons have jumped over to the other side and combined with holes. So no holes, so holes or electrons. So that is why it is a depletion region, depleted of charge carriers. If I apply a voltage though across this, the electrons on this side will get more energy, which can jump over to the other side, overcoming the barrier or the repulsion of this negatively charged layer. So that depending on the energy, you may be able to jump to the other side and widen this depletion region. Or if you apply a voltage in the opposite direction, you may actually reduce it. In other words, you take some electrons from here. Okay, so both is possible. Okay, let me draw that. So if you have, for example, the same piece of semiconductor, right? So if I take this and connect it to a battery like this, so what will happen is this is the positive, this is the negative, and you will, this is N type and this is P type. You already had a depletion layer here. You already had a depletion layer like this. But now what is happening is that you have more electrons here. They go like that and jump here, and they actually combine with this area. So these gets vanished. And similarly, electrons from here gets pulled to this positively charged plate. So therefore, this also gets reduced. So the new depletion layer only this thing. So it's a decreased depletion rate. Okay, decreased depletion region. On the other hand, so this is like basically this is like a diode connected in forward bias. Now, as drawn here, it still does not conduct because still there is a depletion region. So there is still a region where you have an insulator in the circuit, so you cannot actually support a current. If I increase this battery voltage further, what will happen is more electrons will jump and then they will combine with this area where you don't have the electrons also, and these electrons will be taken out, and after that there will be no depletion region, meaning that you can after that support the current. So this is why a diode needs a minimum forward voltage of about 0.7 volts for silicon diodes to have a current. Less than that, there will be no current because of this small but finite depletion region. On the other hand, if you connect the semiconductors to the battery in a different way, right? So you initially had this depletion layer, this white, and now you connect the battery in the opposite direction. Now this is the positive and this is the negative. What will happen now is the electrons here will actually go into this, and now these electrons have more energy because of this external energy source, the battery, and they will be adding to it. Okay? More, the depletion layer is increased. At the same time, the electrons here will be pulled out of this into this positively charged plus terminal of the electrode. So therefore, now the depletion layer has widened. Okay? The depletion region has increased. So this is the increased depletion region. Okay? So this is as if you have connected a diode in reverse bias. Something like this. Okay. So here depletion region is smaller. And it's a little bit more conductive than when it is not connected, right? More conductive. And this is called forward biased. If you make this forward biasing large enough, it will enable it to have a continuous current. On the other hand, on this side, you have an increased depletion layer. In other words, a larger depletion region. And it is less conductive. And this is called reverse bias. And that, no matter how much you apply, it will not conduct electricity because the depletion layer gets wider and wider. What will happen if you make it really large is that there will be enough energy actually to make the electrons jump from this side to this side, which is called breakdown. Okay, so that is called the breakdown. When that happens, the diode will get burnt. Okay, so we are not going into, we don't want to go into that region. Okay, so further increase will break down the junction. Okay, so that we need to keep in mind. Right? Is it clear? Okay, hope it is clear. It's simple enough. Right. Now that we know the basic, we refresh our mind about the basic semiconductor physics of a diode. Now let's see how charge free, that basically holes and electrons inside these semiconductors move around. Okay, so modes of charge motion. Okay, modes of charge motion. How electrons and holes move around inside this semiconductor. There are two processes. Okay, there are two processes by which electrons and holes move inside the semiconductors. Okay, so charges, basically electrons and holes, move due to two processes. One is called the drift. The second one is called the diffusion. This is called, second one is called the diffusion. Okay. So what is drift and what is diffusion? Okay. Now drift is when, if you look at what it is, you kind of have an idea about what is drift and what is diffusion. You know that diffusion, by definition, is basically the random motion of charges in any direction, or all directions. Okay, so there it is not directional. It moves around in every single direction. Whereas drift has a direction. Okay, it is drifted towards a certain direction where you have an energy gradient, right? So if in order to have a drift, you should have an external field applied. It could be an external electric field in terms of voltage applied. If there is an external electric field, positive to negative electric field, then electrons experience a force in a certain direction, and they will tend to move towards that direction. Okay, this is called the drift. And this behavior can be precisely modeled using an equation called Ebers-Moll equation. This current, the motion of the movement of charge, which is basically a current. This current is modeled by Ebers-Moll equation, right? So let's have a look at what that Ebers-Moll equation is. So let's first look at drift. Okay. When an external electric field is applied, the charge can be moved. Okay, electric external electric field means it's a voltage, right? The behavior of charge movement of charge is basically called current. Is modeled by the Ebers-Moll. These are names of two scientists, Ebers and mole. Ebers mole, not small, M-O-L-L. Ebers and mole. Okay, Ebers mole equation. And what is Ebers mole equation? Ebers mole. Oh, for shorten, we say EM equation. Ebers mole equation. So if you have a diode, if the voltage applied across the diode is VD and the current through it is ID, the relationship between these can be written as ID is equal to some reverse saturation current, some current, we'll get to that what it is, okay? Some constant IS times E exponential variable to the power VD, the diode voltage, divided by N times another voltage called VT, which is called the thermal voltage, VT minus IS. Okay, so this IS is called the reverse saturation current, which is basically the diffusion current. Remember, there were two ways of current, so drift current and diffusion current. So this is the diffusion current. Okay, so IS is the diffusion current. It's a very small current, but it is there, whether it is forward bias or reverse bias. We'll get to that. Okay. So let me mark what these things are first. ID is the current through the diode. And VD is the voltage across the diode. And IS is called the reverse saturation current. Okay, and this is typically very small, in the range of nanoamperes. And it also varies with temperature. Vary with T, temperature. As you can imagine, the diffusion depends on the energy of the charge carriers, electrons and holes. With temperature, that energy changes, so therefore the diffusion changes. So therefore the reverse saturation current or the diffusion current changes with temperature, but this is a very small value. Whereas this VT, this quantity over here, okay, VT is called the thermal voltage. This is a thermal voltage, and this is actually, this can be written as VT equals the Boltzmann constant times the absolute temperature T divided by the charge of a electron. So this also depends on the temperature, right? Vary with temperature because we have T, VT, thermal voltage. Vary with temperature. But at room temperature, this is basically what we work with, right? At room temperature, you can put the values in and see the Boltzmann constant and Q for the charge of an electron, and temperature 25 degrees Celsius converted into Kelvin by adding to 273. right? You will see that this value is about 26 millivolts, about 26 millivolts at room temperature. Okay, so we consider it as a constant, and n in this equation, this value here, this n is basically a non-ideality factor. Non-ideality factor. Okay, if things are ideal, if ideal, n is equal to 1, but practically things are not ideal, so therefore n is between 1 and 2. Okay, so this is basically what you have. So if you try to graph picture, draw a picture of the relationship, that is ID versus VD. So this is ID, this is VD. You will see, let's say, if you have very small VDs, in other words, negative VDs, right, in this region, what will happen? Very large values of VD. Now, if VD is much greater than VT, VT is what? 26 millivolts, right? Let's say VD is negative 1 volt or something. Then what happens is this quantity becomes much smaller than this quantity. This quantity becomes the dominating factor, right? So you can put values and see. So you will see that that graph will not change depending on VD. So anything above a certain value of VD, okay, let's say a few orders greater than VT, VT is very small, so few orders greater than VT means in like, you know, as soon as it becomes something like, you know, 200, 300 millivolts in the negative direction, this component becomes negligible. So therefore it will become just minus IS. Remember, IS is a constant, so therefore it would look something like this. Some negative value, something like that. And it will change according to this relationship for small values of negative VD. And for positive VD, in other words, this side, right? In that side, what will happen? IS is a constant. As VD becomes bigger and bigger, this will have an exponential increase. This will have an exponential increase, and this effect of IS will disappear. This term will be much bigger than this, so therefore you can neglect this second term. It will be just that. Okay, so it will, if you plot it, you will see that it looks something like this, something like that. You will see that this is the this positive part is what you saw as the diode's characteristic. The voltage current characteristic is basically that, where this around here you have what is called the forward voltage. Whereas in the ideal case, we assume the diode's output current to be 0, but it is in fact not 0. It's a little bigger than 0, this value, very small in nanoamperes typically, but that is called the IS. This is IS. This is a constant. That is why it's called the reverse. It's in the opposite direction. Saturation current. It is saturated. It doesn't change with the voltage. So therefore, we call it the reverse saturation current. Okay. So that's basically what you have here. This is the shape of the IDVD or the voltage characteristic. So this is basically the diode characteristics, except that since IS is very small, we assume it to be 0. This is not to scale, right? This is not to scale. This side, the negative side, is much expanded than the positive side. Okay, right. So this is basically what you have. Now the good thing about this Ebers-Small equation is that it works for both positive and negative directions of voltage. Right? It doesn't matter whether the diode is forward biased or reverse biased. Now remember, when you analyze diodes, you have to remember, you assume whether it is in the forward direction or the reverse direction. If it is reverse direction, reverse biased, you have to put 0 as the current. If it is forward biased, you have to find the current, or maybe you assume the voltage is fixed depending on the model. But here, if you use Eber-Small equation, you don't have to assume any of that. You put just ID as the current, VD as the voltage, and just do the problem. The only problem here is that this is a non-linear equation. So this is not a linear equation. If you have to find voltage and current, then you have to solve a non-linear equation, a set of equations. So this is the issue, right? But nevertheless, you don't have to worry about knowing about whether it is positive direction or positively biased or negatively biased, right? So works for any region of operation, reversed or forward biased, reverse biased, reverse biased, or forward biased. Both are fine. But note that the current does not increase when the voltage increases in the reverse direction, okay, negative direction. Because why is that? The reason for that is because as you increase the voltage, it increases the depletion region. So though the voltage increases, it also, because the depletion region is increased, it also increases the R. So V divided by R, which is equal to I, does not change. Okay. That is why it saturates. Note that current does not increase. Does not increase when voltage is increased when reverse biased. Because the reason for this is reverse bias will increase the depletion region. And therefore, it will increase the resistance. So I is equal to V over R. V increases, but also the R increases. So therefore, the ratio does not increase. Okay, so that is the reason. Okay, so that's about the diffusion. We know that diffusion, drift. That is about the drift. In drift, you have in the negative direction, or when it is reverse biased, current does not change appreciably. It is constant, a small value, IS. Whereas in the forward direction, it increases rapidly and becomes almost constant as VD increases. Okay, it exponentially increases. That's basically what happens when you increase the current in the positive direction. Right. Now, the second mechanism is called the diffusion. The second mechanism of charge motion is diffusion. Now, this is basically random motion of charges in every direction, right? So this is random motion of charges in every direction. It's like the Brownian motion kind of thing. So by randomly they move in every direction. So what happens is, if you just take a small area across which if you measure the charge motion, in other words the current, you will see that no matter what direction you are measuring, there will be a small current, even in the reverse direction. Even if you have applied a voltage across a diode, even when there is a voltage in the forward direction, there will be a reverse direction current, a very small, minute reverse direction current due to diffusion. But what you see is the difference between this in the direction, right? So this random motion causes a small current, to flow in the reverse direction. And any other direction also, even when there is an external voltage. External voltage applied. And this is the cause of IS. This is the cause of IS. So this is how the reverse saturation current IS is generated, right? This IS is a constant. Depending on many external energy sources, like the heat, depending on the temperature, or if there is any photons impinging on this junction, any other energy source that influences the behavior of electrons, this current, the diffusion current, may change. Okay, so this depends on many external energy sources. Like heat, light, because light has photons, which can be converted into energy, right, etc. Right, so you see, if you externally excite the electrons in the semiconductor, they will have higher energy or lower energy depending on how you apply it. If you cool it down, you'll have less energy. So the amount of energy, depending on the amount of energy, how much diffusion current is applied will depend, right? Remember, the IS is the reverse saturation current. It depends on the temperature, okay, and other factors also. Now, for example, if I want to increase the ID, one way we can increase the ID according to the Ebers-Moll equation is to increase IS. If you increase IS, ID will increase, right? Because ID is directly proportional to IS. However, if I am trying to increase IS using temperature, because I said temperature increases the energy that will increase the diffusion current. So what will happen? Let's see, right? So when temperature is increased, obviously the current has to increase. IS will increase. Okay, that's good, due to increased diffusion. We already know that. But as T increases, what will happen? As T increases, atoms start to vibrate. There's more energy. Okay, atoms start to vibrate. So when atoms start vibrating, they knock each other down, and the electrons find it difficult to go through because it will get knocked off, right? So therefore, what happens is the resistance, this increases the resistance. Therefore, heat is not a good efficient way to increase the reverse saturation current. Okay, because it also vibrates the atoms and increases the resistance. Heat is not a good or efficient, not an efficient way to increase the reverse saturation current. IS. Okay, so this is also called diffusion current. So what will happen if I increase T? If I increase T, it will increase IS, which is what we want, but that will increase ID, exactly what we are trying to achieve. But this also increases RP, R. Because of that, the power dissipation across this I squared R will also increase, much bigger, right? You know, this will increase a lot more. And because of this, I squared R heat is generated. That heat is going to increase the temperature even further. And that is going to increase IS further. That is going to increase ID and R further. And it's going to generate even more heat. So this is going to go into a positive feedback. Okay, this. So therefore, this is called a. So after a while, there is going to be so much heat, the diode is going to overheat and burn. This is called the thermal runaway. This causes thermal runaway. So therefore, using heat is not a good efficient way to increase the IS. But a more efficient method would be to use photons. Okay, in other words, photoelectric effect. More efficient way to increase IS is photoelectric effect. Here, so you apply light, which is basically going to cause increase in photons. And these photons directly transfer the energy to electrons, but not to the atoms, right? So transfer energy to electrons, but not to atoms. Transfer energy to electrons, but not atoms. But not atoms. So more charge carriers with higher energy. In other words, the electrons and holes will have more energy. Okay. So this will cause more electrons. More electrons will be capable to jump over the depletion layer. Okay. More electrons can cross the depletion layer. Which means the resistance is now actually gone down, not increase. Just more conductive. That will actually increase IS. IS will increase without increasing RS. In R, not RS, R, due to atom vibration. So therefore, now we achieved the increasing of IS and thereby increasing ID without more heat generation. So this is not, this is basically an effective way of doing it, but unfortunately, the Eber-Small model that we talked about does not capture this. This behavior is not described by the Eber-Small equation because we are applying light, not external voltage or anything, right? This is not described by the Eber-Small model. So this is called an external, this is an external energy model. This is an external energy model. Okay, an external energy model. There are many other such external energy models, none of which are captured by the Eber-Small model, right? So this is basically, I think, all time that we have. So therefore, we'll stop this lecture here because we have the next lecture. It's actually the same link that I have sent you for the other lecture also. So let me stop this lecture here, and then we'll meet again in the next lecture. So I'm not going to close this, but I'm going to end this meeting here, and we are going to